All right, we're going to talk about the z-score today. Now, don't freak out because it's a z. Just pay attention, and we'll go through it. Now, to help you pay attention today, I wore a bright-colored bow in my hair. It's got nice stripes with green, and you can see... Oh, wait, no, you can't see it. Oh, well, you'll just have to imagine it's got all sorts of rainbow colors and stripes and all those fun things. So hopefully, as you're imagining that will help you to pay attention, or maybe that's a bad thing because you won't be thinking about math. You'll be thinking about the pretty bow in my hair. Anyway, what do we already know? Well, we already know that with probability, all the probabilities of a given situation have to add up to 1, or 100%. Or in other words, probability of 1 plus probability of 2 plus probability of the third, all the way up to the final probability of each specific value. If I add all the probabilities of those individual values, they need to add up to 1. Okay, so from there, we look at the normal distribution. We say, okay, well, if I add up everything underneath this curve, that's all of the values, all of the probabilities underneath, or the area, it should all add up to 100% or 1. Now, in class, we introduced the idea that we've got 68%, 95%, 99.7. We said, okay, those are rules of thumb. And so from there, we want to be able to say, okay, well, these are only approximate, therefore the squiggly equal signs there. And we talked about in class how to do this using the calculator. And using the calculator, you can get that these are not actually 34 for each of these pieces, that they're slightly different. It's 34 point something, something, something. And so that you can use your calculator to get more exact values. Okay, now from there, what we want to do is we want to take our normal distribution curve and not only be able to take a specific standard deviation, but also be able to consider the situation, what if it is not exactly a standard deviation or 2 standard deviations from the middle. And so for this, we do what's called a z-score. So the z-score, z, equals x minus mu over sigma. Now, I know it looks scary and I know it looks weird because there's all those letters, but you already know what those mean. X is the value of our specific point because we're looking at a specific value and trying to figure out the probability that we get that or something less or in between 2 values. Okay, we've got mu. Mu represents our mean, of course, and sigma represents the standard deviation. Now, from there, we consider the idea. Let's see if we can figure out what all this means, what the z-score actually is. Okay, so we start with our value and we subtract the average. So essentially what that does is that tells us how far we are from the middle, right? If we have a large value, then we'll get a positive difference, which means that we're to the right of the mean. Right? So if this is my curve, there's my mean. So here's my value, whatever it is. This is mu, this is x. If I subtract x minus mu, that tells me how far I am. This one will give me a positive value, whereas if I have something down here, that will obviously give me a negative value because I'm going to do a smaller number minus a bigger number, and that will give you a smaller number, which will be, again, the distance from the middle. Now, I'm going to divide that difference, that distance, by the standard deviation. And what that's going to do is that's going to tell me how many standard deviations away I am. If I'm exactly 1 standard deviation away, then the distance will be the standard deviation. When I divide by that, I'll get 1. If it's something a little bit more than a standard deviation away, then I'll get 1.2 or 1.3 times the standard deviation on top. And when I divide by standard deviation, then I get 1.3. What this does is it normalizes the situation. Okay, it's kind of like when we looked back at transformations. We were looking at the parent function, and we always went back to the parent function and based all of our knowledge and understanding and shifting and stretching and everything from that. It's a similar idea with this. We're going to take everything back to a normalized, normal distribution curve. Now, for the normalized distribution curve, that just means, and I don't know why this is, no! Okay, I don't know why this is going crazy. But anyway, with our normalized curve, then the middle, the mean, is considered to be 0. and the standard deviation is considered to be 1. So by doing that, we've kind of have a normalized curve. This is like the parent function of all the normal curves. Obviously, the average can change because we're shifting. Obviously, the standard deviation can change if we stretch or squish our graph. But really, this is the parent function, where the average is at 0 and the standard deviation moves to the right or left. This is going to help us understand the z-score, because a positive z-score means that I'm a positive standard deviation to the right. Negative will mean to the left. So let's see if we can kind of put this together and calculate this. Okay, so this says Kelly scored 73% in history. The class mean was 68. The standard deviation was 10.2. In math, she had other scores with a different standard deviation. The question is, in which subject did Kelly perform better compared with the rest of the class? Well, that's a very good question. If I just look at the data, I've got 73% in history, 68% was the average. So she beat the average by 5 points, but the standard deviation is a little bit bigger, which means the data is a little bit more spread out. So just beating the average by 5 points maybe does or maybe doesn't mean anything. Here we look at the math score. She scored 66%. The average was 62%. And so again, that's 4 points above, but the average was lower. So maybe the average or the mean being lower means that scoring a lower score above that is still better. So what we need is we need something to kind of put all this together and tell me, okay, well, really, how well did I do? Achoo! Wow. Should have seen that one. Anyway, so we've got, what we're going to do is we're going to find the z-score, which will tell us how many standard deviations away we are. So the z-score is x minus mu over the standard deviation. So for history, we're going to find her value, which is her score, 73, minus the mean, which was 68, divided by 10.2, which is the standard deviation. So I'll pull out my handy-dandy calculator, and we'll go 73 minus 68, and then we'll divide by 10.2. Oh, moving too fast. Still too fast. Okay, there we go, 0.49. So my z-score is 0.49. Now what that means is if I had a normal curve with my average and with this being the first standard deviation, so that's mu plus standard deviation, that means I'm 0.49 or about half the way in between. So that's where her score is, right? The 73 and the 68 average, the 73 was hers, so that's how far I am from the middle. So now we'll consider the z-score of mathematics. So again, we'll take her score, which was 66, we'll subtract the average, and we'll divide by the standard deviation. So when we do that, we'll find out that we've got here, let's go ahead and put it in parentheses. So 66 minus 62 divided by 6.8. And we get 0.588, so we'll say this was actually 490, so we'll go 588, which means the z-score here is farther. So even though the values are less, the z-score is greater, which means that I am farther away from my average with respect to the standard deviation, which means there's a greater area below it, which therefore means that this is a better performance than the history compared to everyone else. Okay, so let's go ahead and look at one other example. This is the last one I'm going to go over. Find the mean and standard deviation of a normally distributed random variable x if the probability of x being less than 20 is 3 and the probability of x being greater than 50 is 2. Now it wants us to find the mean and the standard deviation. Okay, well that's important. We can get those values, but those values aren't necessarily related directly to the probability. So what we're going to do is we're going to say, okay, z equals our average minus, our value minus the average over the standard deviation. Okay, and we'll do it again because we've got two different situations. So z equals x minus mu over standard deviation. So let's see if we can use the data given to us in order to be able to solve the problem. So what we're going to do is we're going to find out what the z-score is for these specific values based solely off of the pieces that we have. All right, so let's start with the probability of x being less than 20. Okay, so let's consider this. I've got my normal curve. The average is here. Now the probability of x being less than or equal to 20 is 30%. Well, the probability of it being less than the average is 50%. That means that my 20 has to be somewhere over here, and that the area is 0.3. Okay, now what we're going to do is we're going to somehow relate this to the z-score. Now the z-score, remember, we said in a previous slide, was just the parent function. Okay, now if we can get the probability on the parent function, because the probability in the parent function should add up to 1, then we can also get the probability in the transformed function. Okay, so what we're going to do is we're given a probability and we want a value, but we already know that this value is 20. What we want is the z-score value. So what we're going to do, remember that if we have a proportion or a probability, we can get that from the inverse normal. So I'm going to go into distribution. I'm going to go into inverse normal. So when I do that, it's going to have the area, the average, the standard deviation. So for the area, I'm going to put 0.3. Now, I don't know the standard deviation or the mean, but that's okay because I don't want the overall value. What I want is the z-score. And the z-score refers back to this parent function of an average of 0 and a standard deviation of 1. And so from here, I'm just going to go enter, paste, and find the answer. That right there, negative 0.524, that is the z-score. And so the z-score is negative 0.524 because that is the value when we reference the parent function. Okay, so now I can go negative 0.524 is equal to the value, right? Because the probability, the z is the same. So the value is 20 minus mu over sigma. Okay, so that's my first equation. Now let's see if we can do the same thing with the 50 over here. So I've got my curve. Here's the average. Now it says the probability of it being greater than 50 is 0.2. Well, the probability of it being greater than the average is 50%. So if I want a smaller value, then I'm going to have to come out here, which means this area over here is 0.2. All right? Now that value, of course, is the 50 on the normal curve. Again, though, we want to relate this back to our parent curve, which has the mu of 0 and the standard deviation of 1. So again, we're going to refer back to that. Now, the probability from the normal inverse always gives us the probability that it's less than. So if this is 0.2 above the 50, then what is the probability that it's below the 50? Well, it's 0.8. Okay, because they have to add up to 1, right? So x plus 0.2 equals 1. Subtract and you get 0.8. So we're going to go into our calculator. And we're going to say, okay, again, we want the inverse normal. And this time our area is going to be 0.8. All right. Again, we want the z-score, which means we're going to take it back to the parent function. So average of 0, standard deviation of 1. And when I do that, note that this time I get a positive z-score. That's because I'm above this time, right? So I get z-score equals 0.842. So now I've got 0.842, which is my z-score, is equal to the value, 50, minus the average over the standard deviation. So from here, I've got two equations with two unknowns, And so I can solve that. Now, as long as I've got my calculator, then I may as well use my calculator. So I'm going to rewrite this. I'm going to multiply both sides by sigma and then divide by the z-score. So this will end up as sigma equals 20 minus mu over negative 0.524. And then on this side, I'm going to do the same thing. So I'm going to have sigma equals 50 minus mu over 0.842. So now I've got two equations that are equal to sigma. So I'm going to go ahead and put those into my calculator. Okay, so we're just going to go on over here. And for y1, we're going to put in 20 minus x. And I'm going to need to divide that, so I better put it in parentheses. And divide by negative 524. All right. And then for the other equation, I'm going to put in the other piece here. So I'm going to go 50 minus mu divided by 0.842. All right. This one I didn't have to put the bottom in parentheses because it's not negative, and so it should just be fine. Now, for my window, sigma, remember, is the standard deviation. So if I think about what my standard deviation will be, well, I know that 50 is only 0.842 standard deviations away from the middle, and the middle has to be somewhere between 20 and 50. So it can't be much more than about 20 or so. So let's make our x values go up to, our y values, standard deviation, up to 20. I expect the average to be somewhere between 50 and 20. So let's make those our x values. So x min will be 20. X max will be 50, because I know that my average has to be somewhere in between those. You can narrow it down a little bit more. You can go from 25 to 45 or something if you want to get a little bit closer. And then the y values, of course, is my sigma. And so, again, the standard deviation has to be less than about 10 or 20. So the standard deviation is not going to be negative. So I'll go 0. And y max, standard deviation, let's maybe just guess about 20. And so we graph it. There's my first line. There's my second line. Oh, it's a little bit off the graph. And so all I'll do is I'll go into my window. I need to change my y max. Let's go up to 30. And we graph. And now I can find the intersection of the two graphs. So I go second calc intersect, which is number 5. And first curve is y1. Second curve is y2. And then I don't need to guess because there's only one intersection, and it gives me an intersection. Remember, sigma is the y value, so the standard deviation is 21.96, which is 22.0. Now, of course, once you have that, you should be able to solve pretty easily for mu. And so we'll go ahead and do that. We'll put 22.0 in for sigma. And actually we have mu because mu is the 31.5, and so mu equals 31.5. We solved for x and y, so actually we did them both at the same time. So there you go. We ended up solving for the average and the standard deviation. Keep in mind that the big idea here is that we're taking these values, and rather than looking at them as is, we're taking them back to the parent function, which then means that I'm not looking at the value anymore. I'm looking at the z-score, which is the distance from the average, not necessarily my value anymore. And so once I find the z-scores, then I can set up a couple equations and solve for it. Okay, so I hope that's helpful. If you need to, go ahead and rewind it and watch it again and see if you can get an idea of what we can do with the z-score. All right? Well, that's all, and good luck on your homework.